it doesn't take the video. But that's okay. I'm much obliged.
It takes the video.
It does, eh? Okay, interesting. All right, so I was telling you that here is a command window. You can, type single commands. Like if I said 1 + 1, that's 2. If I said sine of pi, it will tell me what it is. Okay. So in a command window, you can type, single line commands and you get output instantly. Now, up here in the editor, you can write a series of commands and run all of them at the same time. I could, for example, say x is 5 and y is 2 times x. And then I say display y. Okay, so now I can, of course, I can save this script. Let me just save as, you have to choose your location carefully because that becomes your working folder. And we'll see the implication of that in a very short time. Okay, so there we go. So I've saved my script as example. And now I can now see, if I try to run this, it tells me that it hasn't found this in my current folder. So I have a choice. I can add it to the current path, which is my working directory, or I can browse to wherever I have saved it and I make that my working directory. So let me do that. Okay, so that should be it. So now in your current folder, you should be able to see the script that I just wrote. So I can run it. If I run it, because I have this display function, the output comes out in the command window. Now, instead of running the whole script, you can as well left click and select, right click and evaluate. Give the same thing. You can section your code. Let's say here I have z equal to 13, and then I say m is 3 plus z. If I want to just run the upper section of the code, I run section instead of hitting run. If I want to run the lower one, I do the same. All right, so the part of the environment that I've not talked about yet is on your right-hand side. It's called the workspace. And this is where all your variables show up. A useful command is clear. I can clear all. If I clear all, then everything is erased from memory. You see my workspace is blank now. But let me just run this line by line. X equal to 5. Right click, evaluate selection, see what happens to the workspace. It picks up the value and stores it in memory, and it shows up on the workspace. If you want to see the properties of this, do I have a question? Okay, let's go on. If you double click a variable, you see its properties. So by default, if you don't declare a type, it comes as a double. So same thing here, if I run Y, there we go. It also gets saved. Of course, display Y is an output. It doesn't store anything. So when you run it, it outputs something in your command window, and there'll be nothing in your workspace. All right, so basically, that would be it. Comments are preceded by a percentage sign. And I think you know what comments are. It's good programming practice. Okay, so there we go. So know what the workspace does, know what the command window does, and know what your editor does. Another useful command is CLC. That one clears your command window. So that is about the programming environment of Matlab. Any questions so far? Okay, no questions. So let's move on to now DSP specific routines that you're going to encounter time and time again. So of course in DSP we deal with signals, and the simplest signal that you can deal with is a signal that has only one frequency, and that is a sinusoid. And in the latest lecture slides, I think I put a slide or two about sinusoids. You know that the general format of a sinusoid, what some of you call sinusoid, is X, XT, XN. Now, we will mostly focus on discrete signals because we assume that since it's digital signal processing, you have already digitized, you have already sampled the analog input. So if you see me write X square bracket N, that means that's a discrete signal. It has already been sampled. You know the process involved in digital analog to digital conversion. You have an analog signal, and then you have a sampling frequency associated with the sampling time, and then you go through this signal and pick out discrete values, and you quantize those, and then you encode them into digital values. So when I write XN, that's a discrete signal. If I write XT, that's an analog signal. So that's the convention that we shall use all through. So let's go with so XN is discrete and XT is analog. So the general format of a sinusoid, let me write XN equal to amplitude times sine of omega t, omega n in this case. And what is omega? Actually, to make this simpler for you, let's first deal with the analog signal. So xt equal to a sine omega t, where omega is the angular frequency. So that means sine of, what's omega? 2 times, anyone?
2 pi.
All right, so 2 pi
F.
F. And then T. Of course, be careful. Much as you were saying 2 pi ft, there has to be a multiplication between any constants and any variables. So here 2 is a constant, pi is a constant, F is a constant because it's the frequency of a signal, and then T is a variable. Because you're dealing with a time domain here, so you want to see what values this signal is going to take on in a given time interval. And so for you to be able to plot such a signal, it means you need to know what A is. So let's assume that A is given to you and it's 10. So that's the amplitude. It's a constant. 2 is a constant. You don't need it. You don't need to input anything. Pi is known by Matlab. It's a constant as well. Now F is a constant that you need to define. So let's assume that your frequency is what? 10 hertz. Okay. Now, of course, since you're declaring the variable here, you're not going to put units. You're not going to append units to it. Okay, so what else do we need to know? Remember, we need, let me just, all right, so this is what we want to do. So this is the sine signal, and this is the time axis. And so we want to plot something like this. It means we need to know what this, time scale is going to be. So we need a start point and an end point. But more importantly, we need to define this time, I'll call it a time vector for now, that tells us how many samples we need in this signal. Now, I don't know if you guys know anything about sampling, but you know that the more samples you have, then the better for you. If, for example, I had just this sample and that sample, it means I would only be able to reconstruct my sine wave like that. And then it would end up looking triangular. So when your sampling frequency is low, meaning that your sampling period is high, because that's the sampling period, the time between the samples that you're acquiring, then your signal reconstruction is going to be a bit haphazard. So you want a high sampling. I write better than this, but I'm writing on a screen, so do forgive me. You want a high sampling frequency, meaning the sampling time has to be low. Now, as a rule of thumb, they always tell you that if the highest frequency in any signal is F1, then choose a sampling frequency that is at least what?
Twice.
At least twice of F1. Now, this is known as Nyquist's sampling theorem. Of course, at least never cuts it in real life. So at least is the bare minimum. So don't get surprised when I tell you that if right here we have a sinusoid and its frequency we have defined as 10 hertz. So don't get surprised if I tell you to use, but we can also vary this and then you see what the transition is going to be. So I'm going to define my sampling frequency as 100. Now, I've just chosen this as an arbitrary value, and we're going to change it and see what effect it has on my signal. So the next thing I'm going to define now is this time vector. Remember, so let's say I'm starting from 0, and then I'm ending at 799. Meaning, what's the length of n? How many samples do I have in my signal? If I start at 0 and end at 799, how many samples would I have? I would have 800, isn't it? So what I'm trying to bring out is, if you have n samples in your signal, then they will always run from 0 up to n minus
n-1.
n-1, right? Okay. So your samples run from 0 to n-1. But since you're dealing with an actual time scale, remember the difference, the time difference between each of these samples is the sampling time t, which is the same as 1 over the sampling frequency. And so that is why when I'm defining my time vector, I will write that if I want n samples in my signal, capital N, again, let me define it as an arbitrary value. Let's say I want 1,000 samples in my signal. And again, I'll say this is arbitrary. If it's not given, choose a high enough value. The number of samples, the higher the number of samples, again, the better. Then I can say my time axis will run from, let me show you this. So you guys should know about arrays from your programming, from your previous programming experience. So if I wrote, in Matlab, this is how you define arrays. So if I wrote 1 up to 10, it generates an array from 1 to 10, spaced in intervals of 1 by default. If I had written 1 colon 0.5 and then 10, I'll generate an array between 1 and 10, but this time with a spacing of 0.5, and that means I'll have 20 points. 19. Fun enough. Now, so what I want to do here is to say that I want an array from 0 up to n-1. And since I'm talking about time, and we saw that from this formula, Ts is 1 over Fs. If I want to convert this to a time scale, 0 to n-1, I multiply it by Ts, which is 1 over Fs. So that's why I'm defining my time vector, and you may have seen this before, as 0 up to n-1 divided by Fs. Does that make sense to all of us? So why we're doing this is we're trying to generate a sine wave, and you can't generate a sine wave using one time point. You need a series of time points, and that's why you need this time vector. So at each of these times, you will apply the sine function to generate the corresponding value, the dependent value on the vertical axis. And so I can now comfortably write x equal to a, because I know what a is, sine of 2 times pi times f, and then times t. Let me just run these commands. Of course, these are constants. Okay, so we have them there. Let's see what happens when you run this line. So t 0 to n minus 1 over fs. See what that gives us? It gives us a vector of 1,000 points as we had defined. And you can see what is in there. The last value happens to be 9.99. I can ask you why that is so, but that's a question for later. And so now generate the y value array from x equal to a sine 2 pi ft. So let me run that as well. And so we have t and we have x. Now remember, there has to be correspondence between the independent value, which is t, and the dependent variable, which is x. They must be arrays of the same size. And I think you can see it here. All of them have 1,000 numbers inside them. And so we have values for t and x. The next thing we have to do is to plot. Now, the plot command is plot xy. You always write x first and y next. So here we want to plot x against t. So it means we write t first and then x. If you want this to pop out, you can always put a figure behind it, meaning that this plot is going to come up in a new figure. So let me just run this for you and you see what happens. So there we go. Okay, so this is your sine wave. Maybe it's a little bit congested now because it's displaying the entire time axis from 0 to 10. I can limit the time axis using xlim. And I say, no, show me only from 0 to 2. And so if I run this again, you see that it's showing me only from 0 to 2. What can you tell me about this sine wave? What can you tell me about the figure you're seeing? Anyone? Does the sine wave look smooth?
No, it looks like it's being clipped.
Yeah, it looks like it's being clipped, meaning you're losing a bit of information. And why do you think that is so? Any of us? Why do you think that is so? Or do you think there's anything we can do to improve the state of affairs?
I think we use a very high FS.
We should use a higher FS, right?
Okay.
Oh, you're saying we use
FS,
the high one. You want us to go lower?
Because, okay, according to the theorem, it's supposed to be at least greater than twice, but we use like, I don't know, 100 or 1, so it is a very high value. I think that is oversampling.
Oh, okay. According to what you're saying, let me make this 20 and you see what's going to happen. Okay, so let's run this again. Whoa, you see that? Is that better or worse?
Was.
It is worse. So this is what I was telling you about Nyquist sampling theorem. You see, they tell you at least twice for you to be able to recover anything. But for you to recover the signal in its entirety, you should actually go as high as you can. So the fact that even when we had 100, you had some information missing means that 100 is also not good enough. If we made this 500, and remember, this is digital signal processing. The difference between analog and digital signal processing is if we're going analog, then probably would have had to change the value of a resistor somewhere. If it's an already built circuit, then you're not able to do that. But since we're manipulating the signal digitally, all we have to do is just change the value of a constant. And that is it. And the computational time doesn't even change. So let's make it 500 and run this again. So how does it look now?
It looks better.
It looks much better. So of course, you see if your sampling frequency is 500, then it means your sampling time is your period is 1 over 500, which is 0.002. So if I had wanted to display only, let's say 2 periods, I could just clip this to 0.004, and that will display. Oh, no, 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 no. Absolutely not. I take that back. 0.2. Okay, so let's see what the period is here. Of course, you can use the tracking. So if I want to know what the period is, I can use this cursor here. And it's telling me my period is 0.1. Of course, the reason is your signal, your sampling frequency is just for reconstructing the signal. It has nothing to do with the actual period of the signal. So the sampling period and the signal period are different. So the actual frequency of the signal is 10 hertz, meaning its frequency, meaning its period is 0.1. So if you want to display 2 periods, you do 0.2. I hope that makes sense to you guys. So if I start from here, then 1 cycle ends here. And that would be 1 period. And so from 0.1 to 0.2, those are 2 periods. Yeah, so it's important to get that distinction about the signal period and the sampling period. I have a couple of questions here. Let me just let's go here. All right, so David, what are you saying?
What frequency should we recommend?
David, we can't hear you. Unfortunately, we can't hear you. Can you please type your question in the chat? Please type a question in the chat. Betty, you have a question?
Yes, my question is like what we are essentially plotting is like a sampled signal. So is there like some kind of way that you can display the original signal so that maybe you could compare and see what you're actually outputting at the end of the sampling process?
Let me see if I get your question correctly. You see, what we're plotting here is a digital reconstruction of a signal. So maybe let me show you. You can use a stem plot instead of plot. So if I do stem tx, let's see what we get. So that's what the samples look like. Does that answer your question?
Yes. So okay. I don't know, like what does the initial, this is like at each point, like the every single, does this point out the initial signal and then every single point at which it was sampled, or
no. We are right now we are simulating a signal using a mathematical function. This is not a real world signal that we have brought in.
Oh, okay.
Yes.
That makes sense.
Yeah, we're simulating a signal. But when you're acquiring real world signals into a computer, then you must specify a sampling frequency deliberately. And in fact, when I give you some of those real world signals, I'll be telling you this signal was sampled at this frequency. Make sense?
Yes, thank you.
My question is, how do we know the exact sampling frequency since we actually didn't go through the... Oh, to me, it looks like a try and error. No, it's not a try and error. Nyquist already tells you that you need to use at least twice. But what I've just shown you is that at least twice is the bare minimum. It's not good enough. So go as high as you can. And since you're programming, just change the value of the constant. Make it as high enough as possible. For most signals, I would say use a sampling frequency not less than 100. Of course, if I had reduced the highest frequency in this signal, then it means if I'd made this like 2 Hz, if I'd made this like 2 Hz, it means that here sampling frequency of even like 50 would probably give me a good signal. Let's try that. Of course, I'm going to change my limit here. 1, since my period is 0.5. So let's do this. So you see that? That actually gives you a good reconstruction of the signal. Let me comment this out and we visualize the first one. Okay, so that's a good reconstruction. So between you and I, but you see, it's also not very smooth, right? Although it is good enough. So someone says 2, I say go 20 times, at least 20 times, the highest frequency in your signal. Okay, see if I have any other questions. Steven, what say you?
Yes, okay, I'm looking at this, the definition of the time t. Okay, we know it's an array, but when I look at how we define it, it's like it's like, okay, because I think the fs, is it not supposed to be like the interval between successive time at which the samples are taken, but it's like we are dividing. So is this not simply scaling it other than giving that constant interval between like those successive samples?
Oh,
Because
no,
we are
no, 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 no.
dividing.
No, no, we are dividing because what we have is a time scale. It's not a frequency scale. And Ts is 1 over Fs, right?
Yes.
Yeah, so it's like we're multiplying by 1 over Fs, which is the same as multiplying by Ts.
But okay, when you are giving the examples of the array, you show us whereby if you gave that like the interval, because I think we want the interval to be 1 over Fs. So is it not supposed to be in the second column other than multiplying the whole thing by that? Because
No,
isn't
no,
that
no.
really...
Let me show you something here. Okay, I'll close that. I'll just create a new slide here. So I want you to look at this time scale. So assume your period, your sampling period is 0.1, okay? It means if my first signal is here, the next signal is at 0.1, the next signal is at 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Let me just go up to 0.9. So how many points are in here? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so this is my n equal to 10. Okay, my sampling period here is 0.1, meaning the sampling frequency is 1 over 0.1, which gives me 10, right? So if I were working backwards and I were given the sampling frequency, which is 10, and I want to generate this time vector, I would say, oh, I need 10 points, right? Meaning I'm going to run from 0 up to n minus 1, okay? But I know going from each point to the next, the distance between them is Ts, right? So I'm multiplying the whole array by Ts, which is 0 to 9 multiplied by Ts is 1 over Fs, which gives me 0 up to 9 over 10. And so that is how I end up with the first number will be 0 over 10, which is 0. The next one will be, remember I'm going in steps of 1 here. The next one will be 1 over 10, which is 0. The next one will be 2 over 10, which is 0.2, until I reach 0.9, which gets me up to where I want to be here. Stephen, have I answered your question?
Okay, sorry to interrupt, but okay, I get the point. But for this case, our step size, okay, 1 can really give us a close idea of what we're trying to achieve. But I'm imagining now the case for what we're doing, the sampling period, if you calculate, it's about is it 2 milliseconds? That value is small. I don't know if you take a step of 1, let's say
No,
1
no,
divided
no.
by fs can give us that exact value.
No. So when I say n is 1,000 points, then this n is going in steps of 1 because I'm counting the number of samples. So that's going in steps of 1. But you see now, when I'm going to plot on my time axis, I want to convert that scale to the time scale. So I'm saying, okay, 0 to 999. But I know between 1 point and the next one, I'm supposed to have a separation equal to the sampling period. So what is that sampling period? It means get the n array, which goes in steps of 1, and multiply by the sampling period. And that will definitely ensure that what was a step of 1 now becomes a step of the sampling period. So if we go here, we have 1,000 points, and we're saying, oh, if we go to the time scale, we'll have 1,000 points that run from 0 up to 999. But to convert the time scale, maybe let me just do this. Let me just show you. N scale will be 0 up to n minus 1. And then I say the time scale will be n scale times 1 over fs. So you see the n scale is in steps of 1 all the way up to 999. Up to 999. Now, if you want to convert this to the time scale, get that scale and multiply by the sampling period, which is 1 over the sampling frequency. And so that's how you generate your time vector. Does that make sense, Stephen?
Okay, it's fine.
You don't sound convinced, but I think it will make more sense as we go along.
Okay.
Okay. All right, let me see if I have any other question here. All right, okay, so that's it. Okay, so so we generated a plot here of a sine wave. It's a good practice to always label your vertical and horizontal axes and also give your plots a title. And it's as simple as anything you've come across. Use X label. So X label, let's say, is time there. So X label takes a string, and to declare strings in Matlab, you just use the, what are those? Inverted commas? Y label, same thing. So I can say amplitude. And if I want to put a title, I also give it a string, sine wave. Okay, so if I were to do this again, so my graph will now have amplitude and time as labels, and it will have a title. I want you to look at plot options. When someone has a question. Could you please explain the difference between signal period and sampling period? Okay, Right. So this, when you define a sine wave as S sine 2 pi ft, f here is the signal period. Oh, signal frequency. And so the signal period will be 1 over f. When you define the sampling frequency, that's fs, means the sampling period is 1 over fs. So when I was looking at clipping this signal, remember previously we had plotted the entire x-axis, and then I was trying to clip it, and I'm like, okay, so what if I want to just display 2 cycles of the signal? Where should I put my my limit for x? And the answer lies in the period, the actual period of the signal, because here you already displayed the signal, you already reconstructed it, and you're looking at the actual time scale as to how many, okay, what would be the length of the time axis for a given number of cycles. On the other hand, when you're reconstructing the signal, you're looking at the sampling period. So that is why when we're defining the time scale, we looked at the sampling frequency and we used it to generate the time scale. I don't know if that makes sense to you, Derek. So the sampling frequency does not tell you how many cycles are in one period. That's the actual signal frequency that gives that information. Does it make sense to you, Derek?
Yeah, it makes sense.
Okay. All right. Okay, so I want you to look at plot options. For example, if I wanted this to be in red, I could do that. So my plot now should be in red color. If I wanted to oops, no. I think that's a plot style. I don't just put it there. Now, the good thing is Matlab has a lot of, one of the helpful tools you'll find is help. For example, if you did help, pick any function, help plot, it will give you information about that particular function, and it will tell you how to do it, how to use it, and it will also give you a couple of examples. Yeah. So let me, for example, pick marker size. So if I decided to add marker size here and made it 20, marker size is like the thickness of your plot. Oh, no. No, that's not what I want. No, the thickness of the plot is line width. It's not marker size. So if we use 2, see that? If I make it 1, then the plot is going to be thinner. If I make it 10, even thicker. Yeah, so I want you to, take interest in some of these functions that you're going to be using time and time again. Okay, now I want to show you another way of generating a time vector. So let's say I didn't want anything to do with the sampling frequency, and I just want to generate a time scale. I could decide to, there's a function called linspace, and what it does is generate, and if you want to know what linspace is, you can just do help linspace. And it tells you that it generates a raw vector of, or default is 100. X1, X2, N generates N points between X1 and X2. So if I, let's say, wanted to generate points between 0 and let's say 10, and I want to generate 1,000 points. Let me just clear what I have in my variable window. Okay, so if I run this, there we go. So you have 1,000 points, and it picks for you the interval automatically. Now I can straight away, of course, I still need AF constants. So amplitude and frequency. So let's say I again define my my sine wave as that. So I know what A is, 2 pi, F is a constant as well. And this time I just defined a time vector by picking values between two limits, and I picked so many values. Now we want to see if this is good enough. So let's see. We haven't used the sampling frequency. We just did something random. So you see, if you do 0 to 10 and 1,000 points, then the number of points you have in here is good enough to give you a sine wave. But you see, if I reduce the number of points to 500, probably, oh, okay, still works. 200, okay, now things become murky. So it means that if you generate 200 points between 0 and 10, of course, the linspace is going to intrinsically define what the actual sampling period is going to be in there, because the period, the values are going to be linearly spaced. So it means when you lower the number of points you're generating, you're increasing the sampling period, meaning the sampling frequency is going to go lower and lower. So the fewer the points, the less perfect your reconstruction is going to be. Yeah, so that's one other way of generating a signal. Instead of explicitly stating what the sampling frequency is going to be and defining the time vector, just generate some points, a given number of points within a range, and the sampling frequency is going to be automatically defined for you. And you can play around with the number of points and the time interval to generate a suitable sampling frequency and sampling period. Okay, makes sense?
Yes.
Okay. So the next thing I want to show you is what if I wanted to plot two signals on the same graph? So let me just use this. Let me up this again to 500. So I'll define this as x1. And then I define x2, which is another signal. Maybe at half the frequency. So I can say sine 2 pi. This time I write f over 2. And then t. Simple. So I have two signals now. One is x1 at a frequency of 2. The next one is x2 at a frequency of 1. So I plot x1. So if I want to pick up the next plot on the same graph, I use the hold on command. It means hold on to what you have, I'm bringing something else. Hold on to the salad, I'm bringing the beef stew. So I'll do, this time I don't have, because if I call figure again, it means I'll be creating another figure. I want to hold on to that figure, and then this time I'll plot t, remember I'm using the same time axis, and then x2. Right, and of course, I can change the colors. Like here, instead of using line width, okay, that's red. I can just make this one, maybe, let's make it green. And there we go. So it's as simple as that. All I have to do is use hold on. So if I run this section now, you should have two signals. And you can even put a legend. Help. Legend. And this is how you use, of course, a legend is to tell you which signal is which. So, I think the syntax is, yeah, you just put strings following the order of the plots. So all you have to do is just drag this down, legend, sine with frequency of 2 Hertz. Next one is sine with frequency of 1 Hertz. And there we go. So let's see what this does to us. If I run section, there we go. So now we have a legend which tells us which plot corresponds to what. Okay, someone has a question. Does the order of the lines of code matter, or it will read everything and let's say variables duplicated with the code run? Oh, yes. The order does matter. So the code runs sequentially. But before I answer that, do I have any question about this? About multiple plots?
Excuse?
Yes?
How is it able to select that the red sign is one of 2 Hertz and the green one is one of 1 Hertz? Because I see you just write the legend, then how does it figure that out?
Oh, no, it follows the order in which you declared the plots. So you see I plotted x1 first and x2 next. So it follows that order.
Okay.
Any other question? Okay. So someone is asking if the order in which we we write the lines of code and execute them matters. Yes, it does matter. Let me clear variables, clearing my workspace, CLC, clear my command window. So I'm just going to write a few things here. So if I write A as 10, and then I say 2, let's say Z is A times 10, okay? And then I write A equal to 2. What will be the value of A, the final value of A, if I execute this code block?
Two.
Hmm?
2.
It will be 2, right? Right, because, yeah, so the execution is sequential. So it doesn't really matter what you declared A to be before. If you declare it again, it means you're using the same variable name, meaning you're using the same space in memory, meaning you're going to overwrite the current value of A. So if I run this, look at what's in your workspace. The final value of A is going to be 2. Now, one advantage of digital signal processing is of course, it happens so fast. So execution is instantaneous. And by the way, do you know that on the analog side, if you wanted to up the amplitude of the signal, you use an amplifier circuit. Maybe you can do a usual amplifier, you can use an operation amplifier. There's so many ways to do it. But you see, if you're working with a digital signal, amplification is as good as multiplying the amplitude by a constant, and you're done. So if, let me just make this F. So let me make this A times 10, okay? So if I run this, see what I did there? This was your initial signal. This is your new signal. After you have amplified it by a gain of 10. So there 10 stands for my gain, because it's a factor that I've put into my amplitude. And do you know how long this took to execute? It's another trick I want to show you. If you want to know how long a block of code takes to execute, you use TikTok to sandwich that line of code. So pay attention to, oh, what happened there? Okay, so you see that? 0.0005 seconds, which is quite negligible to perform that amplification function. So when you're streaming on YouTube and you increase the volume, intrinsically what is happening behind is digital signal processing. It's just up the amplitude and the volume of your output device increases. As simple as that. Why? Okay. What is Orion saying? Why doesn't Z equal to 20? Because execution is top down, A has a value of 10. Oh, wait a second. Okay. All right. Let's do this again. So Orion, let's do this again. A is 10, okay? Let's run this sequentially. A is 10, Z uses what the value of A is at that point. So Z is 100. And the next line says, oh, overwrite A, change it to 2. We haven't done anything else to Z. So Z is still what it was when it was first calculated. Okay, let's see if we have another question. No, that's it. Steven, does that satisfy you? Okay, so of course, the mathematical functions that you know still apply. If I told you to add these two signals and plot the output. So let's say you have that signal, 2 pi f. Let me actually make this a bit more interesting. X2. Oh, you guys know thing or two about noise, right? So I'm going to generate what I call white Gaussian noise. And by the way, if I give you an exercise and say, generate a white Gaussian signal, all you have to do is go to Google and look up, oh, generate white Gaussian noise in Matlab, and the function will be given to you, and you will even have an example. So these things are not rocket science. So white Gaussian noise. Let me show you what that does. Help WGN. So generate an M by N matrix of white Gaussian noise. P specifies the power of the output noise. The unit measure for the output of that is watts. All right. So as simple as that. So M by N matrix. So since I want a vector, it means I'll put here 1. Remember, it's generating a random signal for you. And so I want this second signal to have the exact number of elements that are in X1. And X1 has 500. But in case you didn't know, you can always do length of X1. And it will tell you the number of elements in a vector. So let me put length of X. Remember, it was saying M by N matrix. So M is 1 because I have 1 row and 500 columns because I want the same number of elements in X1 to be here and 0 power. That's what the function was saying. So okay, this should be X1. And debugging in Matlab is pretty straightforward. It always shows you the line of code that is throwing the exception, and then it tells you explicitly what the error is. Okay, so let me run this again. And out of curiosity, I'm going to do figure plot T X2. All right. So that does look like noise, right? Oh, first of all, do you guys know what white Gaussian noise is?
I think I think telecom people surely know, but I don't know about electric and computer, because telecom people have done courses in communication theory and digital communications.
Okay, okay. So I'll stop making assumptions going forward. So I'll be saying things that I think some of you could be knowing, but if you ever feel that I'm wasting time on something that's obvious, you can always tell me to cut it to the chase. Okay, so yeah, but I'm not going to tell you what white Gaussian noise is, because that's something that you can look up. But it's one of those basic noise models that I use to, somehow show processes, random processes that occur in nature. So white means that it has uniform power across the frequency band. So what I wanted to show here is, remember, this X1 was a pure sine signal. So X2 is noise. And what we want to do is contaminate the signal with noise. And it's as simple as saying, let me just assume this is a system, and I say output signal is X1 plus X2. Now, because I've just added the two, it's called additive noise, meaning it's just added onto the signal to get your output. And so there we go. So we know our original signal, we know the noise, and we have summed the two. And now we want to plot T output signal. Let me just lose everything. Let's comment that out. Comment that out. Okay, so let's see what we have here. All right. So that's a little bit nasty, isn't it? So remember, our original signal was clean, and all of a sudden, you have noise contaminating that signal, and it looks a little bit fuzzy. Now, what if we had started with this signal? Would it be possible for us to work backwards and remove whatever noise? Oh, someone is, could you please mute if you're not speaking? Okay, so there we go. So this is a noisy signal, and in future we will want to work backwards. If you're given a noisy signal, can you, for example, figure out the highest frequency in that signal? Or if you know that, okay, you can figure out the frequency components in that signal and figure out what is the dominant frequency in that signal. You'll find that in most measurement systems, you always talk about electrical noise, which will have a single frequency. Right now, we're doing time domain analysis. We're not doing frequency domain analysis, but frequency domain analysis will be our next topic. Can we figure out the different frequency components in a signal? Can we figure out the dominant frequency? And so when we know these various frequency components, we can be able to isolate the noise from the signal that we want. through a process called filtering. And I think you guys know, you have probably heard of that before. And so we can construct, filters that are designed to fit the purpose. And there are so many frequency dependent filters. You talk about, like IIR, we'll talk about FIR and so many things. And we'll implement all these things digitally. And that is what the digital signal processing is all about. One of the objectives is to manipulate the signal, to clean the signal and remove noise from it. Okay, but what I was trying to demonstrate here is how you can add two signals and plot the output. Any questions? Okay, now if you got to your lecture slides, these are very simple things to understand. If at any one point you feel that you haven't understood anything, you can always raise it when we meet in this introduction to Matlab. So some signals are not as clean as a sine wave, so you will not look at the signal and totally understand it. And so we start, to introduce some other parameters that you can extract, including mean of a signal, sum up all the values and divide by the number of elements in the signal, root mean square value, which is very easy to calculate given a signal. I give you an example there. I'm sure you have heard of power of a signal before. So if you have two signals of different power, then the power in decibels is 10 log the ratio of the power. If you're dealing with voltages, then it becomes 20 log the ratio of the voltages, simply because power is proportional to the square of the voltage, as in P equal to V squared over R. So since R is a constant, where there's P, we can put V squared because the R's are going to cancel for the same system. And of course, log of S squared is 2 log of S, so we can bring the two, we can bring this to, we can bring this here and multiply it into the 10. And that's how we end up with 20 log. So when we talk about signal to noise ratio, we're essentially talking about the ratio of the signal to noise in decibels using the same formula. Usually you want a high signal to noise ratio. So when you have a positive signal to noise ratio, it means signal is greater than noise. When you have a negative SNR, it means noise is greater than the signal. And I give you a couple of examples here. What you have here is like the signal I just constructed for you here. Oh, by the way, you can close all figures by doing close all. But let me just plot this again. Okay, so this signal is similar to what you have here in the first plot. And I would expect the SNR to be, oh, by the way, do you want us to do it? Let's do it. Let us do it.
Yes.
Let us calculate this SNR. So it means we're going to calculate the root mean square of the signal and the root mean square value of the noise. and then use that formula to calculate the SNR. So we know what our so RMS signal is. Now remember, root mean square value means square the signal, find the mean, and then find the square root. So the first thing you do is square the signal, right? So it's x1, x1. Now you, a power is this hat, but since you want to square every element in that vector, you use this dot notation. That's something that you should look out for. So you're squaring, and then you find the mean, and then you find the square root. As simple as that. So that's how you determine root mean square of a signal. So if I found RMS of the signal, or by the, of course, the colon, the semicolon is a terminator. It ensures that what you terminate doesn't show up in the command window. But if I run this without the semicolon, I'm able to see the output in the command window. So RMS of my signal is 7 here. And do you know why it is 7? What is the RMS signal of amplitude 1, of a sine wave of amplitude 1? Do you guys know it? If a sine wave had amplitude 1, if you went through the motions, you'd find that it's 1 over root 2, which is 0.7. So the reason we're getting the RMS value as 7 is because we have. Could you please mute? Okay, so I was telling you, the reason you're getting this as 7.0 is because you have a 10 on the amplitude of this signal. If we didn't have a 10, if the amplitude were 1, then we'd have this as 0.7. But let's go on. So I'm going to just copy this. So this is RMS of the noise. So it will be this time x2. Okay. And then I can calculate SNR as, remember, it's 20 times log of RMS value of the signal divided by RMS value of a noise. And there we go. Okay, and the answer is going to be in dB. So if I run this, let's see what we get. 38 dB, which is really good. It means we have noise, but it's not degrading our signal so much. So what you have here is 10 dB. If you increase the noise, then the SNR reduces. This is 3 dB. That's 3 dB. That's minus 3 dB. That's negative 10 dB. So you see, as SNR reduces, that is slides towards the negative scale on the dB scale, then most of your signal is going to be lost, and you end up with just majority noise. And of course, noise is unwanted signal. You want to minimize that as much as you can. If I had, let's say, multiplied this by 30. Let's see what that gives us. I've multiplied the amplitude of my noise by 30. I would expect my SNR to slide now. You see that? Negative 28 dB. Which is terrible, by all means. Okay, so going on, we talk about variance and standard deviation. Again, very easy to understand. And I show you how you can average for noise reduction, ensemble averaging, correlation. I think you guys know about correlation coefficient. You're trying to see the similarity between two signals. Pearson correlation coefficient, if you normalize it, then it will be between -1 and 1. I'm showing you correlation between two signals here. So this is a sine wave. This is a sine and cosine, sine versus cosine. Now these two signals are completely out of phase. Their correlation is 0. They're totally dissimilar. And such signals are known as orthogonal signals. The correlation is 0. Here we're doing a sine wave and a triangular wave, a sawtooth. And you notice that they are nearly matching, so the correlation is high, 0.9. And here we have a sinusoid and a higher frequency wave, which is a sinusoid, but a little bit, manipulated. And you see the correlation is somewhere in between. Yeah, covariance, the formula is there. I've already defined orthogonality. If you want to know how to calculate correlation in Matlab, it's very easy. Cross correlation means that you're going to repeatedly correlate a reference signal across the entire segment of your signal. I give you examples. Autocorrelation means correlating a signal with itself. Autocovariance and covariance, very easy to understand. And that is it. So I'd expect you to read the things and understand them and discuss. You guys are very sharp. You're the sharpest minds in the country, of that I'm sure. So I want you to finish this set of slides by this week. And then I'm also going to post the first set of Matlab. I'm going to post the first set of Matlab questions shortly. Since it's the first exercise, I'll give you a bit longer to accomplish it. And then I'll also post the next set of lecture slides shortly. Next week is Easter. So we shall not meet, but we can meet earlier in the week if you want. Okay, let's not meet next week. We shall meet the Friday after Easter. So for now, I'll give you time. Those of you who haven't installed Matlab, please do go through this lecture set. Go through all the examples and practice. Get familiar with Matlab so that by the time the first exercise comes around, you are ready. Okay, any questions? Someone is asking if there's multiplicative noise. I wouldn't use that exact word, but yes, there are other noise models. That are not additive, and I'll tell you about them in due course.
Excuse me, sir.
Yes, please, should.
Is in the implementation? if I can, supposing I can do this same exercise, say in Python with Matlab or with any other different environment and language, is my work still acceptable?
It is very acceptable. It is very acceptable.
And
if you can use
concerning the submissions, will we be submitting code and the figures or screenshots of something like that?
I'll give detailed instructions in every exercise, but usually I'm interested in the code snippets. And you can make a report with the code snippets and the graphical outputs. But I'll also expect you to attach your script or any other relevant files.
All right, thanks.
Okay, that's a good one. So if you think, Python, is catching up. The good thing is, okay, Matlab already has all these toolboxes, functions that and a lot of inbuilt help. But for Python, you can always, look up for, packages, DSP packages. They are all over the place, and you should be able to equally do a good job. Someone is asking, won't Matlab slow down our PCs? I don't know. It's not slowing down mine, but in case it slows down yours, then you can try to see if you can share with your colleague. And again, I said you can work together. Just make sure you don't submit the same work. Make sure it looks different when it is submitted. And I'm not talking about editing comments only. I'm talking about looking at work and I see that it is substantially different. Okay, last question. Anyone? So it means that we have to go with our computer. No. The final exam is going to be written. It won't be programming. Yeah, someone was about to celebrate that, hey, they use computers in exams, and no. Okay. So you see, like here, I'm giving you like some, theoretical practice questions. Just make sure you understand the theoretical, But what I usually do is I pump you with as much work as I can and what you can handle throughout this period, because I've never believed that 3 hours of an exam should determine your grade. You can actually be knowing almost all the content and flunk the exam. It doesn't mean that you don't know. So the actual learning happens during the course of the semester. And I think that is what we should emphasize. Yeah, so the final exam is going to be written, but all the coursework, most of it is going to be programming. Okay, so it is 10 a.m. I want to thank you so much for making time for this class, and we will meet again on the 9th of March. But before then, you will have you will have the exercise, the first exercise, which I think now will be due on 9th. I'm going to send it through shortly. So you have 2 weeks to work on that. All right. Happy Easter, everyone.